Hi girls, how are you? So this is the third of the videos on SHM equations, and this one is how those equations are derived using the reference circle. There are three of those equations. There's one for displacement, one for velocity, and one for acceleration. So we've already gone through the graphs and you know what those shapes look like. So this is how you get the displacement equation. So this is when timing starts at 0. So that's where your reference particle is, and this is where the SHM particle is, and after a time t, the reference particles traveled here, and in that same time your SHM particle is traveled upwards and it's there. So the displacement of the simple harmonic motion particle is from equilibrium to there, so it's the length of this blue arrow. In that the angle that the reference particle has gone through is theta. So if I complete that triangle, make it a right angle triangle, this dotted line is the same as this bold arrow here, this vector. So that is y, which is the displacement. The length of your displacement phasor is the amplitude. So if you look at that triangle, your sine theta is opposite over hypotenuse. The opposite is y, hypotenuse is a. So you get sine theta is y over a, or y is equal to a sine theta. And because theta is equal to omega t, you end up with y is also equal to a sine omega t. And that's the equation for displacement at any instant of time when timing starts at equilibrium position. The next one is for velocity. So this is exactly the same thing, but now we're looking at the velocity component. My arrow is not very good, but at any instant of time for the reference particle that's moving in a circle, its velocity, instantaneous velocity, is a tangent to the circle, and it's a constant speed, and the speed is a omega. Okay, and you can see how the direction changes. So when the reference particle goes from here to here, the velocity changes from that direction to that direction, and the simple harmonic motion particle is there, and its velocity is just moving upwards from there. So to put it all together, because in a phasor, using in a reference circle phasor diagram, all the arrows, the tails have to be at the origin. So this is what it looks like. So even though the reference particle is here, its velocity initially is upwards. Okay, and when the reference particle comes there, its velocity is a tangent to the circle like that. So I've just kind of put it over here. The velocity of the simple harmonic motion at all times is the vertical component of the velocity of the reference particle. So when the simple harmonic motion particle is there, this is the vertical component of the velocity of the reference particle. So if you're looking at that triangle here, the reference particles actually move through this angle theta. Okay, and so you have your cos theta is v over omega a. Omega a is the constant speed of your reference particle. So you end up with v is equal to a omega cos theta, or v is equal to a omega cos omega t. So that's your equation for velocity. Okay, and then the last one is your acceleration equation. So acceleration, I got the wrong one first. Okay, this one here first. Sorry. Okay, so this is your reference particle, and when it's over here, acceleration is always towards the center, and when it moves there, the acceleration is still towards the center. So all the arrows, the heads of the arrows, are pointing here. When the simple harmonic motion particle is here and going upwards, doesn't matter which way it's going, acceleration is always downward. But again, in order to get this phasor diagram correctly, the tails of the arrow have to be here. So what I'm doing is I'm just translating it all to the side. So this is what it will look like. So initially, that's the acceleration phasor for when it was at time 0, and after a time when your reference particle is there, its acceleration is pointing to the center, so it's like this, okay? And when your SHM particle is there, the acceleration arrow is pointing down, so this is the vertical component of your acceleration phasor. So just looking at that triangle, because this is the angle through which it is moved, this vertical component is the acceleration at that instant for the SHM particle. So in that triangle, here's your right angle. So your A becomes negative because it's below the x-axis, negative A omega squared sine theta, or A is equal to negative A omega squared sine omega t. So those are your three equations, or displacement, velocity, and acceleration, and that concludes all the little bits for this lesson. And I'll write the notes up, and you need to do those questions, but it's only 3 of those questions which I'll put on my notes for SHM equations, because 3 of them are for when timing starts at equilibrium, and the other 3 are for when timing starts at one of the end positions. All right then, bye for now, take care, be safe.